okay, from your data first, and then you do your fast Fourier transform. Okay, so let me show you the code before I call it a I finished this video. Okay, so how I code this. Okay, I have, this is my custom fast Fourier transform script. It takes in a CSV file, and then it outputs something known as frequency data. Okay, so let's do a clear CLC. Okay, and let me just run it here. Okay, frequency data equals to my FFT, and then it takes in this file, and then it puts out this frequency data. Okay, so basically I have my frequency array here. I have my Fourier transforms here in complex gain form, and actually I have two Fourier transforms because I have one input, one Fourier transform of my input, one Fourier transform of my output. There are two different periodic signals here, which I think I might have shown you before. So, okay, but anyway, the first Fourier transform is the Fourier transform of this input signal, which is the inlet temperature. The outlet temperature will be, the second Fourier transform will be the Fourier transform of this outlet temperature. So that's what this code is doing. So let me walk you through the code. Okay, basically I separate out the code into many functions. So this first function actually is the function that will start running other functions. Alright, so how this works is that I first run the function hello world. I will tell you what those are later. I first run this function hello world. I have a CSV to array function which takes a CSV data file, and it outputs a data array, similar to what we were doing before, except now it's all scripted. I have a print import CSV, which just prints a few lines basically, and it says imported CSV file to array, and then most of the Fourier transforms will be done in this normalized FFT of whatever data. Why is it normalized? Because I divide the new FFT, the non-uniform fast Fourier transform, by the number of data points, which I did not do just now, but it's good to do in case you have more than, okay, let's say I have 20,000 data points, but the more data points you give to the non-uniform fast Fourier transform, you know, the bigger the peaks will be. So those that's by virtue of the summation, okay, and of integrals in general. The more data points you give it, or rather, it's a virtue. It's done by virtue of the summations. The more data points you give it, the more additions that this non-uniform fast Fourier transform can do. That's why the value grows bigger and bigger, and it scales with the number of data points that you give it. So you can just normalize it by dividing by n. I'll show you how that works later. So so this is the first function, and hello world actually just prints a few lines that says hello, this is the FFT function, blah 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 blah. Okay, then the importing the CSV to array, it just does what it says here. We do a read table of the CSV file, and the array is pumped out using this table to array. So read table and then table to array. We pass it back to the function over here. Then we print this bit of code, print import CSV. So it just says, oh, we have finished importing the CSV file into array. And then this one, normalize FFT. Let's go through this code. Okay, so first thing I do is to find out how many data points I have. So n equals to the length of the array. In this case, 20,000 data points. But if you have more, your n will be bigger. Okay. Next thing I need to know is the time interval. Okay, the time interval. Okay. So what's the time interval? I take the last data point of time, which I assume to be the biggest, and I subtract from it the first data point in time. So it's the final time, which is over here. Of course, assuming that as you go down the rows, the time actually increases. So this is the biggest time, and of course this is the smallest time. That is that. So I take the biggest time date and I subtract it from the smallest time. And then what I do next is to say that the sampling frequency equals to number of data points divided by delta t. Okay, where delta t is this time interval. So that's the sampling frequency. How many data points divided by how many what is my change in time. So once I do that, I get a frequency array, and of course I transpose it into column form. That's why I have this transpose over here. This is the transpose step. This is the step where I go from 0 to n-1, and then I'm trying to get an array of frequencies going from 0 all the way up to the sampling frequency. So that's what this highlighted line here is doing, much like I shown you before. Okay, next thing here, I'm going to subtract off the DC component, which was using this trapezoidal rule. So first I define my time vector, and I have a vector for my input and a vector for my output. I get the DC of the input, which is the again using this integral divided by the time interval delta t. So delta t is used a lot of times here, as you can see. So that will give you the average value of the input, just like what we are doing here. Okay, this average value here. Same thing for the output. So I have another Fourier transform I'm doing it. Then just for convenience, I say that the average value of the input is, okay, I print it out, and the average value of the output is, I print it out. That's what you're seeing here, 773, and the average value of the output is 776.7. Okay. Okay, now basically we'll subtract out the DC component. Okay, so input is basically your the time domain data. So I define it as the time domain data minus the DC input. Now this once thing here is kind of not necessary, but I put it there anyway. It's just a habit thing, because MATLAB, other codes may not be as friendly as MATLAB. Okay, so it's good to put this in. So anyway, output is also here. Output equals to output minus the DC component of the output. Now we are ready to do this non-uniform fast Fourier transform. So the normalized non-uniform fast Fourier transform, okay, I put the input in there, I put the time there, and I put the sampling points. Okay, so this is the query points. This is the query point thing, which I was talking about earlier. I divide it by n. Okay, I divide it by n because remember, the more points you give it, the bigger the values of the non-uniform fast Fourier transform. Likewise for the output. And lastly, I have this frequency data, which I have the first column, which is frequency, second column is the input, third column is the output, and that will be returned to this function, and this will go back here, and this will be given as the output of this function. So these are actually several functions working together, but yeah, that's how this non-uniform FFT works. Okay? It's just doing all the steps that I was talking about, and it's scripting it. That's all. Okay, and if you want, you can actually take a look at this data. You can actually plot it out. Okay, you can plot frequency data. Okay, all of it 1, and then at 20 times log 10. Okay, frequency data. Okay, so this is in decibel form. This makes it easier to spot peaks in case there are very different orders of magnitude. Okay, and there you go. We'll have this two peaks, and remember, everything after the Nyquist frequency is actually a mirror of this side. Okay, why is that so? I'm not going to explain in this video, but it's just there. Just know that it's there. The Nyquist frequency is half the sampling frequency. You can see this peak here very clearly shown at 2 times 10 to the minus 3, which is a very good. Of course, if you want to take a look at the output in the example that I given. You can do that as well. Okay, and of course I think I forgot the absolute part. So okay, this is better. Okay, you see that the output is a lot more, this is like a more real signal because there's a lot of noise. Now what you can see is that you know, the signal here is at 2 × 10⁻³ Hertz. Is actually much bigger because this is in a log scale. Remember, this is in a log scale. This is actually maybe like 10 times bigger than all the neighboring points. And in the without this log scale, you're not able to see all these other peaks here. But this can so-called be like considered noise. But you can see that some bits of the noise are a bit bigger than the others. Okay. All right. But anyway, that's what I have. Shown you how the non-uniform fast Fourier transform works. I think I'm a bit over time. But yeah, really over time. Okay. But anyway, that's how the script works. Okay. Thanks for watching. I'll see you guys again. Bye bye.